Back in April of 2026, a team at the Potsdam Institute for Climate Impact Research dropped a paper that, without much fanfare, quietly redrew the map of what's still possible for our planet's climate and what might already be off the table. The finding was buried inside a broader study about carbon cycle feedbacks, published in the journal Communications, Earth and Environment. And here's the headline takeaway. If the Atlantic Meridional overturning circulation collapses, it will not recover for as long as the concentration of carbon dioxide in the atmosphere stays above 350 parts per million. That number should stop you in your tracks, because right now we're sitting at roughly 428 parts per million, and that figure isn't holding steady. It's climbing by about 2.5 parts per million every single year. For context, we blew past the 350 mark way back around 1988. So according to this research, we've been living on borrowed time above the recovery threshold for nearly 4 decades already. The team behind this, led by a researcher named Danian, working alongside colleagues Matteo Willalate, Nico Vundeling, Andre Ganapolski, and Johan Rockstrom, used something called an Earth system model of intermediate complexity, nicknamed Climax X, to run their simulations. Now, what does intermediate complexity actually mean? Basically, this kind of model doesn't try to painstakingly resolve every single square kilometer of the planet's oceans and atmosphere the way a full-blown global climate model would. It trades away some of that fine-grained detail, but in return, it buys something incredibly valuable: speed. It can simulate thousands of years of climate evolution instead of being limited to a handful of decades. And that's exactly the kind of horsepower you need when you're trying to trace out what scientists call hysteresis loops, these long, slow, irreversible transitions between different states of a system, because processes like that unfold over centuries and millennia, not over a human lifetime. So here's how the experiment played out. First, the researchers ran their model using pre-industrial carbon dioxide levels, around 280 parts per million. At that concentration, the Atlantic circulation behaved exactly the way you'd expect a healthy, resilient natural system to behave. Push it hard enough, and yes, it collapses. But ease off that pressure, and it bounces right back. One stable state, clean recovery, no permanent damage. Think of it like a trampoline. You can push it way down, but the moment you let go, it springs back to where it started. Then the team cranked up the carbon dioxide levels in the model, and at 350 parts per million and beyond, something fundamental changed in the underlying physics. The circulation flipped into what scientists call a bistable regime. Instead of having just one stable configuration, it now had two. The first was the familiar state, the one we currently live in, where warm water flows northward, sinks in the high latitudes, and returns southward at depth, ferrying enormous amounts of heat toward Europe and shaping weather patterns across half the globe. But the second state was a collapsed one, where that entire circulation pattern had essentially shut itself down. Here's the part that should really give you pause. Once the system crosses the threshold between these two states at today's elevated carbon dioxide levels, it doesn't bounce back. It stays locked in that collapsed configuration. The door that leads back to the world we know simply does not reopen, not on any timescale that matters to anyone alive today, or their children, or their grandchildren. And it gets worse from there, because a collapse of this circulation doesn't just stop the transport of heat around the planet. It also knocks out one of the ocean's most important jobs, absorbing carbon dioxide from the atmosphere. The same study found that if the Atlantic Meridional overturning circulation shuts down, it would flip the Southern Ocean, currently one of the most powerful carbon sinks on Earth, into a carbon source instead. Over the following centuries, that reversal alone would release enough stored carbon to push atmospheric carbon dioxide levels up by another 47 to 83 parts per million, completely independent of anything humans do. That, in turn, would tack on roughly 0.2 degrees Celsius of additional global warming, stacked right on top of whatever warming triggered the collapse in the first place. This is a feedback loop in the truest sense of the word, a collapse that feeds itself, propagating forward with absolutely no additional human decision required to knock over the next domino. Now, here's the crucial thing to hang on to amid all of this. the Atlantic Meridional overturning circulation has not collapsed. It is still running today. Instruments out in the Atlantic Ocean are still detecting warm water moving north and cold water sinking and returning south. The system is weaker than it used to be, measurably slower than it was just 2 decades ago, but it is still functioning. Picture it like a heavy old door that's still swinging open, still letting air through the gap, but the hinges are getting stiffer and creakier with every passing year. The Potsdam research isn't claiming that door is about to slam shut tomorrow. What it's telling us is that we've already stepped into a hallway where once that door does close, there's no handle waiting for us on the other side to let ourselves back in. So the real question hanging over the Atlantic circulation right now isn't really about timing anymore, it's about mechanism. What's actually driving this system in the first place? What exactly is weakening it? And critically, how would we even know if we were approaching that point of no return before it's too late to do anything about it? Let's talk about the conveyor belt itself, because understanding how this system works makes all of this click into place. Every single second of every single day, roughly 17 million cubic meters of water are moving through the Atlantic basin as part of one giant interconnected circulation. Oceanographers measure that kind of volume in a unit called the Sverdrup, and 1 Sverdrup equals 1 million cubic meters of water flowing per second. To put that in perspective, every river on planet Earth, all of them combined, the Amazon, the Nile, the Mississippi, every last one, dumps water into the ocean at a combined rate of about 1.2 Sverdrups. The Atlantic Meridional overturning circulation moves more than 14 times that amount in one continuous loop that stretches from the southern hemisphere all the way up to the seas around Greenland and back again. And in terms of raw energy, the heat that this circulation hauls northward comes out to roughly 1.3 petawatts. To give you a sense of scale, that's approximately 25 times the total power consumption of the entirety of human civilization, all at once, moving continuously. There is nothing else on the surface of this planet that shifts that much energy around in a single ongoing process. The mechanics behind it are surprisingly elegant once you break it down. Warm, salty water near the ocean surface gets carried northward from the tropics, largely through the Gulf Stream, which is really just the most visible and energetic stretch of this much larger global system. As that warm water travels up into the high latitudes of the North Atlantic, particularly through the Labrador Sea between Canada and Greenland, and through the Nordic seas north of Iceland, it starts losing its heat to the cold air above. And because that water is already salty, thanks to intense evaporation back in the tropics, it becomes extraordinarily dense. Dense enough, in fact, to sink. And sink it does, plunging down to depths of 2 to 4 kilometers before beginning a long, slow return journey back south along the ocean floor. That sinking motion is the engine that drives the whole system. It creates a kind of pulling force at the surface that draws more warm water northward to replace what just sank, which then cools and sinks in its turn, and the entire cycle just keeps perpetuating itself. The end result is a continuous transfer of heat from the tropics up into the North Atlantic, and that transfer single-handedly shapes the climate of an entire hemisphere. It's the reason winters in cities like London, Oslo, and Reykjavik are far milder than their latitude has any geographical right to be. Now, the person who first cracked open the mathematics behind all of this was a physical oceanographer named Henry Stommel back in 1961. He sat down and built what amounted to a thought experiment, a simplified model of ocean circulation using 2 connected boxes, one representing the tropics and the other representing the high-latitude North Atlantic. Then he asked a deceptively simple question. What happens if you vary the temperature and the saltiness of the water flowing between those 2 boxes? What he discovered changed how we think about planetary systems forever. The circulation didn't settle into just one equilibrium. It had 2. There was a state where the circulation ran vigorously, warm water flowing north, cold water sinking and returning south, essentially the world we live in today. And there was a second, entirely separate state where the whole system had effectively shut down, with little to no deep water formation happening in the North Atlantic and virtually no northward heat transport left to speak of. Both of these states were stable in their own right. Once the system settled into either one, it tended to stay there, unless something came along with enough force to flip it over into the other configuration. This was one of the very first demonstrations in any branch of Earth science that a planetary scale system could behave not like a thermostat, smoothly and gradually adjusting itself in response to changing conditions, but instead like a light switch, flipping abruptly between two distinct states with barely any warning in between. And the physical reason behind that switch-like behavior came down to one simple ingredient: salt. The circulation imports salty water into the North Atlantic, and that saltiness is precisely what makes the water dense enough to sink in the first place. So if something comes along and weakens the circulation, say for instance a massive influx of fresh water pouring in from melting ice sheets, then less of that salty water gets imported into the region, which in turn makes the surface water in the sinking zones. That feedback loop feeds on itself, and it does not need any outside help to keep going. Warmer water is less dense, so it sinks less easily. Less sinking weakens the overall circulation. A weaker circulation drags less salty water northward, and less salt arriving up north makes the surface water even less dense, which means it sinks even less. Round and round it goes. Oceanographers have a name for this vicious cycle. They call it the salt advection feedback, and it is the reason the Atlantic meridional overturning circulation does not just gently slow down and then quietly recover on its own. It is the reason this system can actually flip from one state to another, almost like a switch instead of a dial. For decades, Henry Stommel's famous two-box result lived mostly inside the world of elegant theory. It was a beautiful idea on a chalkboard, but the real ocean is staggeringly more complicated than two boxes connected by a pipe. So the big open question was this: does the actual, physical, present-day Atlantic circulation genuinely have two stable states the way Stommel's simple model predicted? Or is that bistability just an artifact? A strange side effect of oversimplifying something as vast and messy as an ocean? That question stayed open for a long time. Then, in March of 2026, researcher Henk Dijkstra at Utrecht University published a sweeping review in the journal Wire's Climate Change. He and his team traced the evidence for this two-state behavior across the entire family tree of climate models, starting from Stommel's original toy boxes, moving up through what scientists call intermediate complexity Earth system models, and finally arriving at the most detailed, most computationally expensive global climate models that exist today. His conclusion, in plain terms, was this: the evidence supporting the idea of two stable states has grown substantially over the last several years, and the present-day Atlantic meridional overturning circulation genuinely sits inside a regime where that bistability applies. In other words, the collapse state is not some hypothetical corner case. It exists. It is physically reachable from where the system stands right now. This is not a theoretical curiosity confined to simplified models on a whiteboard. It is a real feature of the actual ocean we live next to. And part of why scientists feel so confident about that is a simple, sobering fact. This circulation has collapsed before. Roughly 12,900 years ago, as the last great ice age was finally loosening its grip and temperatures across the entire northern hemisphere were climbing steadily upward, something went catastrophically wrong. A massive pulse of fresh water, almost certainly released from the draining of glacial Lake Agassiz, a body of meltwater roughly the size of a small sea that had been pooling up behind the retreating Laurentide ice sheet, poured into the North Atlantic. The influx was enormous, and it did exactly what Stommel's model would go on to predict 6 decades later. It diluted the salty surface water sitting right where deep water formation happens, shut down the sinking process, and collapsed the circulation entirely. The consequences arrived with genuinely shocking speed. Greenland ice core records show that temperatures there plummeted by roughly 10 degrees Celsius within a matter of decades, possibly within a single human lifetime. Imagine living through a childhood with mild winters and watching your grandchildren shiver through conditions nearly as brutal as an ice age, all within one family's memory. Europe was thrown back into near glacial conditions. Pollen records pulled from soil and lake sediments across the continent show forests retreating back into open tundra. Archaeological evidence even suggests that the Natufian culture in the Levant, a group of people who had been experimenting with some of the earliest forms of settled agriculture in human history, was forced back toward a nomadic, foraging lifestyle as rainfall patterns fell apart around them. That cold snap has a name, the Younger Dryas. It lasted roughly 1,300 years before the Atlantic circulation abruptly restarted, with temperatures snapping back upward almost as fast as they had originally crashed down. And here's the unsettling part. The Younger Dryas was not even a one-off freak event. Further back, during the depths of the last ice age, the Atlantic circulation flipped on and off repeatedly in a series of events known as Dansgaard-Oeschger oscillations, abrupt warmings that unfolded over mere decades, followed by slow, gradual coolings that stretched out across centuries. Each one of these swings has been linked directly to changes in the strength of the overturning circulation. The ice core record contains at least 25 of these events spread across the last glacial period. Every single one of them is a reminder that the Atlantic circulation does not behave like a dimmer switch that slides smoothly up and down as conditions change. It behaves more like a system with distinct positions, a system that can jump between states rather than glide between them. So when a research team in 2026 found that this collapse becomes essentially permanent once atmospheric carbon dioxide climbs above 350 parts per million, they were not describing some brand new, never-before-seen kind of risk. They were describing an old and familiar one, a risk the planet has already demonstrated in living geological memory. But this time there was a new and deeply uncomfortable twist added to the story. The real possibility that, under today's atmospheric conditions, the very same kind of restart that ended the Younger Dryas and rescued the planet from that deep freeze might simply not be available to us anymore. So naturally, the next question becomes urgent. Is the circulation actually approaching that threshold right now, in our own time? And the answer to that question hasn't come from a single dramatic discovery. It has been arriving piece by piece, patiently, from instruments bolted to the floor of the Atlantic Ocean. Let's talk about what the ocean floor has actually been telling us. Since 2004, scientists have maintained a line of instruments stretched clear across the Atlantic along the 26.5-degree north latitude line, running from the coast of the Bahamas all the way over to the Canary Islands. These instruments are anchored to the seafloor and connected by cables reaching from the surface down to depths beyond 4,000 meters, deeper than most submarines are rated to travel. This network is called the Rapid Array, and it was built to do something that had literally never been done before on a continuous basis: measure the full strength of the Atlantic overturning circulation in real time, year after year, capturing not just the surface currents that satellites can already track from space, but also the deep, slow, cold return flow moving along the ocean floor that carries the other half of this enormous conveyor belt story. For nearly 2 decades now, those instruments have been quietly recording, and the picture they've assembled is not ambiguous in the slightest. Across the period from 2004 to 2023, the Rapid Array measured a clear weakening of the Atlantic Meridional overturning circulation, an overall decline from roughly 20 Sverdrups down to about 15 Sverdrups, a unit oceanographers use to measure the volume of water moving through the system. That represents a significant decade-over-decade trend, translating into a substantial fraction of the total flow simply vanishing over less than 20 years. The deep water that is supposed to be forming up in the North Atlantic, sinking because of its density, and then traveling south along the ocean floor, is doing all of that noticeably less vigorously than it was when scientists first lowered those instruments into the water. The trouble, though, has always been that a single line of instruments strung across a single latitude can only tell you so much. The Atlantic Ocean is enormous, and this circulation operates across the entire basin, from the tropics up toward the Arctic. A decline measured at 26.5 degrees north could, in theory, just reflect some local shift in that one particular stretch of ocean, rather than a true basin-wide change. So in April of 2026, a research team led by Chanjuan Sheng and Shane Elipot at the University of Miami published a study in the journal Science Advances that looked at the whole question from a much wider angle. Rather than relying on the Rapid Array alone, they pulled together long-term data from 4 completely separate mooring arrays positioned along the western boundary of the North Atlantic, spanning all the way from 16.5 degrees north up to 42.5 degrees north, essentially covering the tropics, the subtropics, and the mid-latitudes all at once. These arrays use pressure gauges anchored at depths beyond 1,000 meters to measure something called cross-slope pressure gradients along the ocean bottom, which turns out to be a reliable way of tracking the strength of the deep overturning transport from below, almost like reading the ocean's pulse from underneath rather than from the surface. And what they found was striking. The decline was not confined to just that one line at 26.5 degrees north. It was showing up consistently at all 4 locations, stretching from the tropics right up into the mid-latitudes, and the pattern held together across that entire span, meaning the weakening wasn't some local quirk tied to one particular monitoring site, but a genuine signal running through the entire western boundary of the Atlantic Ocean. Shane Elapott described that western boundary as the canary in the coal mine for understanding what is happening to the whole overturning circulation. And Rene van Westen, a researcher who wasn't involved in this particular study, said it provided strong observational evidence that the present-day Atlantic circulation is indeed declining, not just fluctuating naturally. The genuinely worrying part, he added, is that the very same climate models whose predictions are now being validated by this real-world observational data are also the models predicting that the circulation is heading steadily toward a tipping point, one where it eventually shuts down entirely. And the mooring data wasn't the only fresh piece of evidence to land in 2026. A completely separate reconstruction effort, carried out by a researcher named Lee and colleagues, used what's called a physics-based water mass transformation framework. That approach combines direct ocean temperature and salinity observations with atmospheric reanalysis data in order to rebuild the entire recent history of the circulation's strength from the ground up. Let's dig into the numbers because this is where the story gets genuinely unsettling. Researchers pulled together data going all the way back to the year 1940, and what they found was a sustained weakening across the entire Atlantic basin starting around 1960. We're talking about a total decline somewhere between 16 and 23% of the circulation's overall strength. Think about that for a moment. Imagine a conveyor belt that's been running your factory floor for decades, and now it's operating at maybe 3/4 power, sometimes less. That's the scale of change we're dealing with in one of the planet's most important heat distribution systems. But here's the part that should really grab your attention. It's not just that the circulation has weakened, it's the shape of that weakening. The rate at which the Atlantic meridional overturning circulation is slowing down appears to be speeding up. It's not a straight, gentle slope downward, it's a curve that's bending steeper over time. And there's a geographic clue buried in this data that makes it even more concerning. Down in the South Atlantic, measured at about 34.5 degrees south latitude, scientists saw this decline show up roughly 20 years earlier than it did in the north. In other words, the southern half of the ocean basin got a head start on this weakening trend, which raises an uncomfortable question. If the South is leading the North by 2 decades, could what's happening down there right now be a preview, a kind of sneak peek at what the North Atlantic is going to experience within the next 20 years? Now let's shift to a completely different method of investigation, because scientists don't just rely on one data source, they triangulate. A separate team of researchers took a totally different approach. They tracked the age of deep water in the North Atlantic using chemical tracers. Specifically, they used 2 compounds called chlorofluorocarbon-12 and sulfur hexafluoride. These substances get absorbed into the ocean at the surface, and then, if the deep water forming machinery is working properly, they get dragged down into the depths by sinking water. Here's the logic. If deep water formation is vigorous and healthy, the deep ocean stays relatively young because fresh surface water loaded with these tracers keeps getting delivered down there constantly. But if that formation process slows down, the deep water starts aging because there's less new water coming in to replace what's already down there. If you want an analogy, think of it like a swimming pool with a filtration system. If the pump is working hard, water is constantly being cycled through, filtered, and refreshed. The pool stays clean and the water is essentially always new. But if the pump starts failing, the water just sits there, getting older and staler because nothing new is flowing in. That's essentially what's happening to the deep Atlantic. Scientifically speaking, this method is basically the mirror image of radiocarbon dating. With radiocarbon dating, you measure the decay of a substance to figure out how long ago something was buried or died. Here, scientists flip the logic. They measure how much of a known surface tracer is still present to figure out how recently that water was last in contact with the atmosphere. A researcher named Guo and colleagues did exactly this, analyzing tracer concentrations across the North Atlantic from 1985 all the way through 2021. Their conclusion? The deep waters are, generally speaking, aging. And that is exactly the signature you'd expect to see if the overturning circulation is losing strength. The surface water that's supposed to be sinking down and refreshing the deep ocean simply isn't doing its job as effectively as it used to. Now let's talk about the Gulf Stream itself, because this is where things get visually dramatic, something you could theoretically watch from space. In February of the year 2026, researchers Van Westen and Dijkstra published a study in the journal Communications, Earth and Environment that for the first time at this level of detail connected the physical position of the Gulf Stream to the overall health of the overturning circulation. Using a high-resolution ocean model, they simulated a full collapse of the Atlantic Meridional overturning circulation and then watched, step by step, what happened to the Gulf Stream throughout that process. What they discovered was a two-stage response, and it's a fascinating one. First, as the overturning circulation weakened gradually over the course of centuries, the Gulf Stream near Cape Hatteras, that's off the coast of North Carolina, slowly drifted northward, moving about 133 kilometers over that long stretch of time. But then, roughly 25 years before the actual collapse hit, something abrupt happened. The Gulf Stream suddenly jumped, shifting an additional 219 kilometers northward in just 2 years. Picture a river that's been slowly meandering for generations, and then suddenly, almost overnight in geological terms, it lurches sideways into a completely new channel. That's the kind of jump we're talking about. The researchers argued that this abrupt jump could actually serve as a physically observable early warning signal, something visible from satellite orbit that would tell us the deep circulation is approaching its tipping point. And here's why this matters far beyond the world of computer modeling. The satellite record we already have shows the very beginning of this exact pattern playing out in the real world. Satellite altimetry data collected from 1993 through 2024 reveal a statistically significant northward trend in the Gulf Stream's position near Cape Hatteras. And subsurface temperature measurements, which stretch all the way back to 1965, confirm the same pattern independently. Altogether, the Gulf Stream appears to have shifted north by approximately 50 kilometers over just the past 30 years. To be clear, nobody is claiming that the sudden, dramatic jump has happened yet, but the slow, gradual drift that precedes that jump in the models lines up remarkably well with what our instruments are actually recording out there in the real ocean. It's like watching the first few pebbles roll down a hillside before a landslide. Not proof the landslide is imminent, but definitely not nothing either. All of these separate threads of evidence converged dramatically in April of 2026, when researchers Valentine Portman and Didier Swingadow, working alongside colleagues at the University of Bordeaux, published a study in the journal Science Advances that tried to answer a deceptively simple question. What happens if you take the future projections that climate models produce for the Atlantic Meridional overturning circulation, and then you correct those projections using what the real ocean is actually doing right now? In other words, stop trusting the models blindly and start grounding them in observed reality. To do this, they used 4 different observational constraint methods. The most effective of these was something called a ridge-regularized linear regression, essentially a statistical technique that pulls together a huge set of real-world measurements to filter out the systematic biases baked into the models. And the answer this method produced was striking, a projected weakening of the overturning circulation of 51% by the year 2100, with an uncertainty of only plus or minus 8%. To put that in perspective, that's roughly 60% stronger than what the average of the uncorrected, unconstrained climate models had been predicting. That's a massive difference. The equivalent of finding out your car's brakes are wearing out 60% faster than the manufacturer's estimate suggested. And where did this correction come from? Largely from one specific source of bias. The climate models were getting the salinity, the saltiness of the South Atlantic wrong. And that's precisely the variable that multiple other studies have flagged as one of the most important indicators for how close this entire system is to reaching its tipping point. So when you step back and look at everything that emerged between 2024 and 2026, you see direct observations, historical reconstructions, chemical tracer analysis, satellite records, and now observationally corrected future projections, all of them pointing in the exact same direction. The Atlantic Meridional overturning circulation is weaker than it used to be. It has been weakening steadily for decades, and the best available estimates suggest it's going to weaken considerably further before this century is finished. Where reasonable scientists actually disagree is what happens at the very end of that weakening curve. Does the circulation settle into some kind of diminished but stable holding pattern, or does it cross a threshold and collapse entirely? That disagreement is real, it's rooted in serious physics, and it absolutely deserves to be understood on its own terms. So let's talk about the case for resilience. Because not every researcher who looks at this same data reaches the same dark conclusion, and their reasoning deserves serious attention because it's built on solid physics, not on wishful thinking or denial. In February of 2025, a team led by Jonathan Baker at the United Kingdom's Met Office published a study in the journal Nature that pushed 34 different climate models to genuine extremes, including a quadrupling of atmospheric carbon dioxide and a massive dump of fresh water into the North Atlantic, essentially simulating a worst-case scenario. And here's the striking result. In every single one of those 34 models, the overturning circulation weakened significantly. But in not a single one of them did it fully collapse. Why not? Baker's team pointed to the Southern Ocean as the key player. Down around Antarctica, powerful westerly winds circle the continent and drive a persistent upwelling of deep water. That upwelling has to be balanced out by sinking water somewhere else on the planet, and in practice, that somewhere else is largely the North Atlantic. This isn't optional. It's basically a law of physics, a consequence of mass conservation. Whatever comes up around Antarctica has to come back down somewhere, and the shape and geometry of the world's ocean basins essentially funnels that requirement straight onto the Atlantic. So as long as those Southern Ocean winds keep blowing, and there's no strong reason to expect them to stop, some degree of sinking continues in the Atlantic, keeping the circulation alive in a weakened but still functioning state. Interestingly, in most of these models, a compensating overturning circulation did start to develop in the Pacific Ocean as well, almost like a backup system kicking in. But it turned out to be far too feeble to actually take over the job, which meant the Atlantic still had to shoulder at least part of the load. Based on all this, Baker concluded that a full collapse of the circulation within this century is unlikely. But this conclusion didn't go unchallenged. Stefan Rahmstorf, who has spent decades studying the Atlantic Meridional overturning circulation, pushed back hard on how this finding was being framed. He pointed out that the wind-driven component of the overturning circulation that survives in Baker's models has actually been understood since the 1990s. It's a shallow, mechanically forced circulation, driven basically by wind pushing water around near the surface, and it simply doesn't carry anywhere near the same climatic weight as the deep, density-driven thermohaline component, which is the part actually responsible for transporting the bulk of the heat around the planet. It's specifically that deep thermohaline part that has a genuine tipping point. Rahmstorf offered a vivid way to think about this distinction. Saying the overturning circulation hasn't collapsed just because a shallow, wind-driven remnant survives is a bit like saying a river hasn't dried up because there's still some dew clinging to the rocks beside it. Technically, there's still some moisture there, sure, but functionally, the river as you knew it is gone. And this distinction isn't just academic nitpicking. It matters enormously for real-world outcomes. European temperatures, the behavior of monsoon systems across the globe, and the ocean's fundamental ability to keep absorbing and storing carbon dioxide out of our atmosphere. There's also a more skeptical voice worth taking seriously here. Susan Lozier, an oceanographer at Georgia Tech, has raised a different kind of caution, and it comes from the observational side rather than from inside the models. Her argument is that the simple story we keep telling ourselves, fresh water goes in, the circulation weakens, end of story, isn't holding up as cleanly against real-world measurements as the models predict it should. There are newer, subtler pieces of how this circulation actually behaves, including the way salinity and temperature interact with each other in ways that go far beyond simple dilution. Picture stirring cream into coffee versus stirring cream into coffee that's also being heated and cooled from underneath at the same time. The second version behaves in ways the first one simply can't predict. Lozier's point is that this complexity might be providing a kind of buffering effect, a shock absorber, that the models aren't fully capturing. And to be clear, these are legitimate scientific arguments, not wishful thinking. The honest picture here is genuinely messier and more uncertain than either the doom-laden headlines or the reassuring ones would have you believe. But there's one structural problem that cuts across almost this entire debate, and it deserves its own spotlight because it's not a small technical footnote, it's a crack in the foundation. The majority of the climate models used in the current generation of global projections, the ones known collectively as the Coupled Model Intercomparison Project Phase 6, including the very study from Baker that argues for resilience, simply do not include the fresh water pouring off the melting Greenland ice sheet. And here's why that matters so much. Greenland's melt is one of the primary engines expected to push this Atlantic circulation toward its tipping point in the first place. Leaving it out isn't a rounding error. It's like assessing whether a bathtub is going to overflow while ignoring the fact that someone left the tap running. This is a real gap sitting right underneath the projections that argue most confidently for a stable, resilient future. So here's where both camps actually agree, and it's worth being precise about it. Nobody credible is arguing the circulation is stable or strengthening. Everyone agrees it is weakening, and everyone agrees it's going to keep weakening. The disagreement is about the destination, not the direction. Does this system settle into some new, reduced but survivable state? A weaker version of itself that still functions? Or does it cross a line and collapse outright? And here's the part that should really shape how we think about this. The consequences of guessing wrong are not symmetrical in either direction. Decision theorists have a name for this kind of scenario, a fat-tailed risk. It means the probability of the worst outcome might be modest, but if it happens, the impact is so enormous and so irreversible that it swamps any ordinary cost-benefit calculation. You don't need to be certain a dam is about to fail before you decide it's worth sending someone to inspect it. This circulation moves heat on a planetary scale, and that single fact changes how seriously we should take even a moderate probability of collapse. So let's actually walk through what that collapse would look like on the ground, because the modeling has gotten specific enough now to put real numbers on it, and those numbers deserve to be heard clearly. Northwestern Europe would take the most immediate and dramatic hit. Winter temperatures across the British Isles, Scandinavia, and the North Sea coastline would drop by somewhere between 5 and 10 degrees Celsius, and the extreme end of that range is genuinely severe. A study published in 2025 in the journal Geophysical Research Letters found that under a medium emission scenario combined with a collapsed circulation, winters in London could see cold extremes approaching negative 20 degrees Celsius, and Oslo could plunge to something like negative 48 degrees. To be clear, those aren't the new average winters, those are the brutal outlier years, the kind that show up once every so often, but they'd be arriving in a world that has built its housing, its farming, its power grids, and its entire infrastructure around the assumption that the Gulf Stream will keep delivering tropical warmth to their doorstep the way it has for thousands of years. In these simulations, sea ice actually extends down to the coasts of Scotland and eastern England during winter, something that hasn't happened since the depths of the last ice age. Rainfall drops sharply across the region too, and a 2020 study published in the journal Nature Food concluded that an Atlantic circulation collapse could lead to the widespread shutdown of arable farming across the United Kingdom, with agricultural losses an order of magnitude larger than what's projected from ordinary climate change alone. Think about that for a second. Not a bad harvest year, but potentially the end of growing crops in large parts of a country that currently exports food. Now, the consequences for the tropics get far less airtime in most coverage of this topic, and honestly, they deserve a lot more. There's a band of rising air and heavy rainfall that wraps around the planet near the equator called the Intertropical Convergence Zone, and its position is partly controlled by the temperature difference between the northern and southern hemispheres. Right now, this Atlantic circulation keeps the north relatively warm, which pulls that rain belt northward, and that northward pull is exactly what delivers the West African monsoon down into the Sahel region. If the circulation collapses and the North Atlantic cools dramatically, that rain belt shifts south, and the Sahel, a region that depends on that monsoon for nearly all of its yearly rainfall, dries out. This isn't a hypothetical worry tucked away in a distant future. The Sahel is already semi-arid, sitting right on the edge. A sustained southward shift of that monsoon could tip it toward outright desert, and the knock-on effects for food production, for mass migration, and for political stability across West Africa and well beyond its borders are genuinely hard to overstate. We're talking about hundreds of millions of people whose water and food security are tied directly to a rain belt that a collapsing ocean current thousands of miles away could shove out of position. Along the east coast of the United States, the mechanism is completely different, but the outcome is just as concrete. Normally, this circulation carries water northward and away from the coastline. If that transport shuts down, the water instead piles up along the shore, and as that stagnant water warms and expands, the same way mercury rises in a thermometer, it could add as much as 1 additional meter of regional sea level rise stacked right on top of whatever global sea level rise is already happening from melting ice and warming oceans everywhere else. For cities like Miami, New York, and Boston, that's not some abstract number on a graph. That's streets, subway systems, and neighborhoods. And it doesn't stop at the Atlantic Basin. The monsoon systems across South and East Asia are linked to Atlantic heat transport through what scientists call atmospheric teleconnections, essentially long-distance links in the atmosphere that connect weather patterns across entire oceans. Those monsoons would weaken and become more erratic, with consequences for agricultural cycles that feed billions of people. Billions, not millions. Underneath every one of these individual impacts sits a bigger, structural concern that researchers have only really started to put numbers on in the last few years. Nicholas Wunderling at the Potsdam Institute has described this Atlantic circulation as the strongest interactor among all of the planet's climate tipping elements, because it links ice, ocean, and atmosphere together in ways that connect systems that would otherwise look completely unrelated to each other. A collapsing circulation doesn't stay neatly contained within the Atlantic Ocean. It changes the conditions under which the Greenland ice sheet melts. It changes how much rainfall the Amazon receives. It changes how much carbon the Southern Ocean is able to absorb. Each of those systems has its own separate tipping dynamics, and the collapse here would push several of them closer to their own thresholds simultaneously. That, in a nutshell, is what cascading risk actually means. In the language of complex systems science, this circulation functions like a hub node in a network of tipping elements. When a hub node fails, it doesn't just remove one piece of the system. It changes the stability conditions for every other system plugged into it. It's a lot like how the collapse of one major bank can ripple through an entire economy in ways that have nothing directly to do with that bank's own balance sheet. The damage spreads through connections, not through the original point of failure. So given how serious both the evidence and the counter-arguments are here, the obvious question is, what is actually being done right now to figure out which side of this debate is closer to correct? And the answer is more encouraging than most people realize. In 2026, an international group of climate scientists launched the design phase of a new initiative called the Tipping Point Model Intercomparison Project. It's the first coordinated global effort to systematically compare how different climate models simulate this kind of Atlantic tipping behavior. Up until now, individual research groups have essentially been running their own separate collapse simulations, using their own models and their own assumptions about future emissions. And that setup makes it genuinely difficult to know whether disagreements between studies are revealing something real about the physics of the ocean, or whether they're just artifacts of how each individual model happened to be built. This new project is designed specifically to close that gap by running identical, standardized tipping experiments across multiple different models at the same time, so that any differences in the results can be traced back to real scientific disagreement rather than to inconsistent methods. Its first results aren't in yet, but the fact that this kind of coordinated infrastructure now exists at all is meaningful on its own. It's basically the tipping point equivalent of what the Coupled Model Intercomparison Project has long done for mainstream climate projections. Not a single definitive answer, but a structured, shared framework for comparing answers so that the sources of disagreement become visible, traceable, and eventually solvable. And the observational side of this story is sharpening in parallel, too. In February of 2026, a research effort was underway that would add fresh, real-world measurements into this exact conversation. Down near the Canary Islands, research crews have just pulled in the latest batch of readings from the Rapid Mooring Array, and this edition extends what is already the longest continuous measurement record we have of the full Atlantic Meridional overturning circulation. Think of it like adding another year to a decades-long diary the ocean has been keeping about itself. Every extra year of data makes it easier for scientists to pull the real signal out of the background noise of natural variability. And the next few years of readings from this array are going to matter enormously, because they'll help determine whether the decline we've measured so far is speeding up, leveling off, or simply wobbling around some new normal. Then there's the Gulf Stream itself. The work done by researcher Van Westen has handed the scientific community something it never had before, a physically grounded stand-in for the state of a deep ocean circulation system that is otherwise completely invisible from space. Satellites can track the Gulf Stream's exact position along the east coast of the United States with impressive precision. And here's the thing to watch. If the slow, gradual drift northward that's been observed over the past 30 years suddenly speeds up into the kind of abrupt jump that shows up in the computer simulations, that would be about the clearest warning flare available, telling us the deep overturning circulation is closing in on its tipping point. Now, whether any of this scientific insight arrives in time to actually change how the story plays out is a question that has far less to do with physics and far more to do with politics. The Intergovernmental Panel on Climate Change, the National Aeronautics and Space Administration, and the United Nations all agree on one thing. The window for an effective response demands immediate, concrete action on three fronts simultaneously: cutting emissions at their source, building real physical resilience against the changes that are already locked in no matter what we do, and reforming our food systems, land use, and economic policies from the ground up. Climate scientist Rahmstorf has put this about as clearly as anyone possibly could. The point, he says, isn't whether we're certain this collapse is going to happen, because we're not with full confidence. The point is that the consequences of being wrong are so enormous and so permanent that we need to be able to rule this scenario out with near total certainty, and right now we simply cannot do that. Consider the cost math here. Preparing for a collapse that never actually arrives, insulating homes, diversifying agriculture, investing more heavily in ocean monitoring systems, that cost is real, sure, but it's manageable. It's the kind of bill a modern economy can absorb. But the cost of being caught completely unprepared for a collapse that does arrive, with the Southern Ocean flipping from a carbon sink into a carbon source, the Sahel region drying out into full desert, and European winters plunging by what could amount to a decade's worth of extra degrees of cold, that is a cost no after-the-fact adaptation program on Earth could realistically absorb. And underneath every bit of this discussion sits quietly a number that opened this entire story: the The finding from the Potsdam Institute study showing that carbon dioxide levels are already above 350 parts per million, a threshold we've been sailing past for nearly 4 decades now. Every additional year of continued emissions is another year in which the underlying conditions for irreversibility get locked in more firmly, just waiting for the circulation itself to finally cross its breaking point. The Atlantic Meridional overturning circulation is still running. The instruments are still sitting in the water, gathering data. The models keep getting sharper and more refined. And the question of whether we're watching a simple weakening trend or the opening act of a full collapse is being actively worked on by some of the sharpest minds in all of Earth science today. All of that is true, and all of it genuinely matters. But here's what's also true. The door to recovery is already narrower than most people realize. This entire circulation system has been running in something resembling its current form for roughly 11,000 years. It kicked back into gear after a cold snap known as the Younger Dryas, and every single human civilization that has ever existed has grown up entirely inside the climate that this circulation maintains. The rainfall patterns, the mild European winters, the monsoons that feed hundreds of millions of people across Asia and Africa, the ocean currents that quietly redistribute heat across half the planet. None of those past civilizations ever had to worry about whether this system would keep going, simply because none of them had the power to disrupt the very conditions that keep it alive. We are the first generation in all of human history that does have that power, and we're possibly also the first generation that will have enough advance warning to actually see the consequences coming before they hit. The moorings are recording. The satellites are watching the Gulf Stream drift, inch by inch. The climate models are, for the first time, being tested rigorously against one another. But whether any of this scientific effort translates into action fast enough to actually make a difference, that's not a question the ocean can answer for us. That question belongs entirely to us.